Hi, I'm Andrea, and this is my part 2 of my evidence 1. Solve problem number 1. A ball is tied at the end of a rope and swings in a circle at a constant speed, doing 60 revolutions at a minute. Where is the frequency? Which period does this movement have? Okay, remember, we have to know first our data, that is the 60 revolutions times meter. We need to convert this, already do it, and it's 2p radians per second. Now we're going to identify our data, that in this case we're going to use this formula, that is frequency, it's equal to W over 2p. Remember that we already have this, the W, that in this case it's this, and we already have the 2p. Always we're going to divide over this, okay? So we just pass, and 2 over 2, remember we just need to eliminate this p and this p, and it's 2 over 2, it's equal to 1 over 1, and it's 1. We just have to put the radians and the seconds, and this is our final result. Problem number 2. The times of a tuning fork having a vibration frequency of 300 Hz, an amplitude of 2.2 millimeters, what is the speed in the displacement is 1 millimeter. This is easy. You just have to convert the millimeters to meters. I already do it, and it's 0.0022 meters. Remember, we have the hertz, we have the millimeters, and we are looking for this specific number. Okay, we're going to use this formula, that it's velocity, it's equal to 2p times frequency times amplitude, and this is our result in 1 millimeter. Problem number 3. A spring is compressed at a distance of 35 millimeters. If its constant is K equal to 190 newtons over meters, what work does the compression force of the spring perform, and what is the potential energy acquired by the spring? Okay, we have to identify our data, that it's the constant, and it's our millimeters, but I already changed it to meters, okay? So we know that work, it's equal to force times distance. So we're going to use the formula F, it's equal to minus K, that it is our constant in this case, and X, that in this case, of course, is our distance. It's equal to 190 times 0.35, and this is our result. Remember that force is always in newtons. So we're going to put the value in newtons. Problem number 4. It says, a metal wire with a mass of half kilogram is a half meter long, and it is subjected to a tension of 100 newtons. What is the speed of transfer wave length to the wire? Okay, we just have to identify that it says that it's half kilogram. So in this case, we are not going to put the 1000 kilogram complete, so we're going to put 0.5. And also it says that the longitude it's that is half meter, so we're going to put 0.5 also. In this case, they gave us tension, but we're going to take it like force. So in this case, this tension and force, it's the same, okay? So we are going to first get our kilogram over meters, that we're going to use the formula that is M, it's equal to mass over longitude, that it's 0.5 over 0.5, and give us 1. Next, we're going to get the velocity, that it's equal to root of K over M. So in this case, we also know that our force is it's K, it's our constant, and we already have the mass, that it's here. So we have both, so we can solve it, that it's first of all 100 over 1, and we're going to get root and give us 10 meters per second. Number 5. Find the mass of a 4 meters rope subjected to a tensile strength of 300 newtons, maintaining a shear wave speed of 150 meters per second. Okay, first of all, we have to identify again our data. Remember that is the most important thing of this video, because with this we are be able to know what formula we have to use. Okay, so we have to pass it to know our mass. Mass, it's we're going to identify what data we have, that I already have it, our mass, wavelength, and we have our length. Okay, so we're going to multiply, and this is our final result. Pass it to know our mass. Mass, it's we're going to identify what data we have, that I already have it, our mass, wavelength, and we have our length. Okay, so we're going to multiply, and this is our final result. Problem number 6. How long it takes for the sound to travel through a piece of road 2.5 meters long if it is made of copper? The density of 8,800 kilograms over meter square, and the modulus of velocity is 1.17 times 10 to the 11 pascals. So first of all, we have to know our data. I've already said we have our density, we have our length, and we already have the modulus velocity. I put it like this, but it is known as a y. Okay, so remember that. So first of all, they are asking us to get off velocity, and then with the formula of velocity we have to dissipate the t. So easy, we're going to use this formula, that is velocity, it's equal to root of the modulus velocity over density, and it is 1.17 over 8,800, and it gives us this result. So we are going to identify what other formula we can use to have the time, that in this case is length over velocity, it's equal to time. So we already do it, and time is 6.866 times 10 minus 3 seconds. Problem number 7. Sound from a 55 dB horn is measured at a distance. What is the intensity of the sound in work over meter square? So we have to know that dB is equal to 10 to the exponent minus 12 work over meter square. So we just have to multiply 10 exponent minus 12 times 55, and then it's two ways to put our result. One of them is in decimals, like this, and the other form it's exactly the same. So we just don't put these zeros that we have here, and we put it instead the 10 minus 3. A car has a radio on and emits 560 Hz while it moves with a linear. A car has a radio on and emits 560 Hz while it moves with a linear speed of 60 kilometers per hour. At first, it comes closer to a person who does not move, and then goes away from it with the same linear velocity. What frequencies are those that the listener who did not move from the same place hears? Okay, we have to identify what we have, that in this case we have frequency, and we have velocity in kilometers per hour, so I change it to meters per second. So we're going to, we want to know the frequencies. When the train goes away, and when the train comes closer to the here. Okay, so we're going to use this formula. 550 times 343, that is our velocity, over 343, that is velocity again, minus 16.666, that is our velocity. And in the second equation we're going to do exactly the same, but in this time instead of subtract, we're going to add. Okay, we are going to add 343 and 16.666. So our results, we're going to divide it. In this case, we have the result that it's different from here. It's this and it's this. So our first result, when the train is closer to the here, it's 588.3532 hertz, and the other result, it's 533.828 hertz, and it when the train goes away. Finally, problem number 9. The city subway advances to 72 kilometers per hour and sounds a 330 Hz horn when passing through an intersection where there is a stationary observer. What are the frequencies of the sound that the observer hears when the metro passes by? Okay, we're going to do exactly what we do in the last problem. We have to convert. Remember, we always have to convert to meters per second because it's easily to you to understand this. We also have the frequency in hertz. So we're going to do exactly the same, that we're going to multiply 330 times this constant, and that is the constant of the sound, over 343, that is the constant again, times 20. In this case, remember that we are going to divide, and this is our first result. In the second way to do it, because they are asking us for two frequencies, one when it is closer and one when it goes away, remember we are going to make exactly the same, but instead of add 20, we are going to subtract 20, okay? So in this case, we have exactly the same instead of our result, that in this case it's 350.432 Hertz, and it's when it comes closer. Thank you for watching this video. I hope it could be useful for you, and you can watch more of my videos here in the link. Thank you.